Well, hey everybody, welcome to another episode of Master the NEC, where we talk about the National Electrical Code, and of course, all things electrically related. My name is Paul Abernathy, your host, and welcome to the podcast. Now, today's episode is going to be a very specific episode about grounding and bonding of a certain condition. And so, as you guessed, we'll be in Article 250, and we're going to kind of start out with the basics so we can get a basic fundamental understanding. And then we're going to move in to some more interesting details of a specific situation that comes up a lot. And I want to address it because I've been asked by a listener of our podcast to address this issue. And of course, I see this all the time with engineers. So not that it's totally engineer driven specific, but I see it all the time. And so I want to talk about what's allowed, what's permitted, and why they might be doing something, and the fallacy behind it. And again, all of those are leaving you wondering what the world I'm talking about. But I am going to tell you what it is after this word from our sponsor, and then we will get into today's meat and potatoes of Article 250, grounding and bonding, right after this. Today's show is sponsored by ElectricianPride.com. Your one-stop shop for electrician-specific t-shirts, hoodies, phone cases, mugs, die-cut stickers, leggings, and so much more. Featuring unique designs for electricians, journeymen, and master electricians, as well as electrical engineers and electrical inspectors. For more information on all the products that are available, visit us at www.electricianpride.com today. All right. So again, thanks for everybody who visits electricianpride.com and looks at the t-shirts and stickers. We got some great Tesla stuff over there, some great Code Mafia. Join the Code Mafia. We got that over there. So Code Wizardry, bunch of different stuff over there. So check it out. Again, electricianpride.com. All right. So today's episode, we are going to talk about a situation where sometimes people are designing systems where you have parking lot lighting, or maybe it's street lighting, or maybe it's street signs. And we're specifically talking about a case where you do have an overcurrent protected device upstream. So these are branch circuits typically that are going out to these different loads. And more often than not, there are pole lights in a parking lot, or pole street signs or whatnot. And again, the premise here is there is some overcurrent protection. So we're not going to talk about a utility situation where they're feeding it and it might be something unique to them because, again, they're outside of the scope of the NEC. So we're talking about a situation that is directly related to where we've had branch circuits that are running out, and there's overcurrent protection upstream, and it might be for parking lot lighting, things like that. I have actually seen it for sign lighting as well, which again, signs in Article 600 has its own unique rules. But at the end of the day, there's a condition where a lot of times, and back in the olden days, they used to run simply a grounded conductor and an ungrounded conductor, hot and a neutral, if you will. And they would not run an equipment ground. And they would say, just drive a ground rod. And because they fundamentally don't understand how and why they're doing it. And that the fact that the overcurrent protected device needs an effective ground fault current path of a low enough impedance to facilitate the operation of an overcurrent device in a ground fault condition. But to be honest with you, an overcurrent device is overcurrents based on three principles: short circuit, ground fault, and overload. So if you don't set the device up properly in order to be able to do its job, it's not going to do its job. And it is certainly not the manufacturer's fault. Okay. Now, of all those conditions, overload could take place again, based on the actual load and what's going on that would cause it eventually to trip the device or blow the fuse. But in general, that's what overcurrent is. It's looking for those three concepts. Now, we only throw that on its head when we look at 695 for fire pumps. And if you haven't listened to our podcast on fire pumps, go check that out. But in that situation, it's a little different because the overcurrent, we're not trying to get anything to do with overload. Okay. We're basically looking for short circuit type of protection on that scenario. But anyway, that's a different podcast. So go listen to that if you want to learn more about fire pumps. It's a 5-part series. It's free. You can listen to it on any of the major podcast platforms: Spotify, iTunes, iHeartRadio, Apple Podcasts. All you got to do is just search for our channel. Just go to Master. Just type in Master the NEC podcast, and you'll find it. And of course, you can listen to that, or you can come over to our YouTube channel and listen at youtube.com/Master the NEC. I share them all there as well. You'll know because it'll say podcast right on the thumbnail. But of course, you can also listen on our website, masterthenec.com, if you want. Also over on electricianlive.com if you want as well. You can always listen to our stuff straight from the website. Doesn't matter what device you use. All right. So anyway, so we're going to be talking about that today and addressing the issue of driving ground rods at light poles. Now, let me get this out of the way. It is not prohibited from doing that, but it is prohibited from using it as the method of grounding or even bonding that light pole or for that circuit. And it certainly is not going to help remove the issue in an overcurrent situation, whether it's a ground fault, short circuit, or whatnot. It has nothing to do with that. Okay, so we're going to kind of cover that today. But again, I'm not going to totally throw my engineering buddies under the bus, because there is practical applications for towers and things like this where basically they're trying to discharge out a certain amount of voltage and subsequent, because of differences of potential current, into the earth so that it doesn't reverberate into the system or cause other side effect problems to the system. So they design their systems uniquely different. I'm not to talk about that today. What we're talking about is the use of ground rods at things as simple as light poles, street poles. Again, all under the understanding that we're talking about they're on the load side of an overcurrent protective device. What are they putting the ground rods in for? What is their reason? And we'll talk about some of those things today in this episode. But again, I always want to use the opportunity to teach you a little bit about grounding and bonding. It's something that I'm very passionate about. I learn something new every day when it comes to grounding and bonding. And being a member of Code Making Panel 5 is just awesome. Just some amazing minds that are over on that committee. And to be able to sit in there and chime in with them and share thoughts and hash things out and have little breakout meetings. And again, this COVID thing is really throwing a crapper into that, because I really enjoy our get-togethers so we can have these little discussions. But anyway, we will overcome, as everybody has here in 2020. And we get ready to start our meetings here in the next couple weeks, I guess, for our code panels that we serve on for the 2023 edition of the National Electrical Code. Yes, we're moving forward. 2023 is getting ready to get started for that development cycle. In fact, it's already started. You've been submitting public inputs, and of course it's over now, but now we get to the work of looking at all of them, and that's the fun part begins, okay? All right, so let's talk a little bit about grounding and bonding in Article 250. So you have to understand that there's a scope, and there's a scope to every article. But when it comes to Article 250, the scope is extremely important because it sets the tone. It sets the tone of what Article 250 actually covers, with the understanding that there are other applications within other articles and sections in the NEC that could change something that's in Article 250, could modify it, could supplement it. For example, 680, 680.26, equipotential bonding. Okay, it does something in addition, over and above what you might have in Article 250 or Part 5 that deals with general bonding. And so, again, a little bit different. And it will supplement it or modify it for that specific situation. It's a beautiful thing if you think about how they're intertwined. Okay? In the code, if you stop and think about it, of all of the codes that are written out there, and again, I am not a fan of UL standards. I'm not a fan of how they're written. They even use terminologies in there that do not jive with the NEC. Okay? So, I mean, they don't even call equipment grounding conductors in the UL standards. Equipment grounding conductors, they usually call them the grounding conductor or something like that. And again, it doesn't really harmonize with it, and because it doesn't have to. It's their own standard. I get it, but again, if you're an NEC person and you start digging into the UL standards, you have to stop and you have to read them again. You go, okay. But again, that's for products. Okay, and the NEC is a minimum safety standard for the electrical industry. So two different things. I get it. But most of the time, the people that are on one committee also serve on the other. So again, there is overlap there. So again, personally, I think the NEC is written beautifully in its function. Not everything is easy to understand, but it's written in its function and how it's laid out is a beautiful thing. Okay, so as you can tell, I've made a career on the NEC, and so it's just a beautiful document. Okay, and I'm always excited when the new one comes out. I'm like, okay, it's new code. Look through it and see, flip in your front and see your name in the front. Again, not for everybody, but I'm just saying it's cool. It forever will be there, even though I die or go to some other, or I leave a committee. It's always there at a certain point in time. You did that. You've done that. So it's pretty neat. Anyway, so let's look at the scope of Article 250 so we can kind of firmly plant ourselves in what we're talking about. So scope of 250 is 250.1. It says this article covers general requirements for grounding and bonding of electrical installations and the specific requirements in 1 through 6. So I have a 1 through 6 here. And basically, to paraphrase it for you so we don't have to go through everything, it says that systems, circuits, equipment required, permitted, and not permitted to be grounded, because we do have those occasions in here where something is required to be grounded, permitted to be grounded, and then, of course, there's situations where it says it is not to be grounded. Covered all in Article 250. That's an amazing thought. It's giving you that kind of direction. It also talks about the circuit conductors to be grounded on grounded systems. It also talks about the location of all grounding connections. Of course, 250.8 talks about the type of connections. It's an amazing thing. Types and sizes of grounding and bonding conductors are all covered in here, whether it's 250.66 for sizing of grounding electrode conductors to 250.102 for sizing of grounded conductors and bonding jumpers, system bonding jumpers. Just a all over amazing concept. Or 250.122 for sizing equipment grounded conductors. All of those vital, fundamental things that work in tandem with other devices to ensure a safe electrical system, all covered in Article 250. Next, again, it talks about the methods of grounding and bonding, gets very deep into that. And then again, it says conditions under which guards, isolation, or even insulation may substitute for grounding, where you might have an application where it talks about the allowance of a double insulation application that, again, is in lieu of grounding. So there's so much that's in 250. This is why this is one of the hardest articles for people to wrap their head around. Not to mention it's one of the longest. It's one of the most in-depth. But this is why I tell people, look, you can bridge that curve by getting a course like ours on grounding and bonding. We have a course that you can get from our website that really digs into it systematically from the very beginning, talking about things like objectionable currents and explaining what objectionable currents is and the methods to alleviate objectionable current in 250.6. And it just literally will systematically take you all the way up through 250, so that when you get to the end and you're starting to look at all the aspects in 250, that you even get up into DC systems and look at all those requirements. It's just an amazing scope of the importance of grounding and bonding. And of course, a good program like our grounding and bonding program will cover that. And so check that out if you're interested in getting a real in-depth understanding of grounding and bonding, which everybody should. This is not for exam prep. This is real life. Over at masterthenec.com, check it out. Or you can also go to the Electricians Academy at electricalinstructor.com, and we have courses on grounding and bonding, and there's some of my favorite courses to work with because of the concepts of grounding and bonding, which people screw up all the time. Okay, now you have that scope, but then another important aspect to this part one, which is general and kind of gets glossed over, is 250.3. And 250.3 is firmly telling us that there are other applications in the code or other articles and other sections that might have something that will modify or supplement or have its own unique rules for grounding and bonding that you have to be aware of. So you just can't go studying Article 2. That's what makes it so vast, is you can't just study Article 250 and take in the full scope of what grounding and bonding is all about. Because if you look at the table of 250.3, all of these articles, all of these sections, all have some type of component that deals with grounding and bonding that might supplement or modify what is listed in the requirements of Article 250. And they might be very much specific and germane only to that situation. For example, healthcare facility in 517. So in 250, it tells you that equipment grounding conductors can be bare, covered, or insulated. However, there's certain areas in a healthcare facility, for example, well, it says no, the equipment grounding conductor will only be insulated. And it will only be green if it has insulation. So again, changing things. Another example of that is maybe in 680. When you're dealing with pools, spas, hot tubs, you have something that's very unique when it comes to permanently installed pools, for example, is equipotential bonding. And that is in 680.26. Well, that bonding is going to be slightly different than what might be covered in Part 5, which is titled Bonding in Article 250. It might be something different. It's going to add to that. It's got its own unique characteristics that you have to think about. And so it's just, 250 is to me, and it's made this sounds really geeky, but 250 of any article in this code book is my most favorite and what I like to dig in the most, because again, you can look at something and in grounding looks straightforward, and then you look at it and you realize they've done it wrong. They've created parallel paths, or they size something, or they don't know the concept of why we do what we do with grounding and bonding, or people take it too far and they go beyond the minimum standard, which you can always go above a minimum standard, but you take it so far that you think you're doing better by bonding this to that or doing something, and now you've potentially created a hazard because you want to do the right thing, but you just went too far. And that's why it takes a healthy understanding of grounding and bonding. Okay. And again, people get hurt if you don't do grounding and bonding properly. And the thing about electricity, it just flows. It just runs, right? It just works. I'm sure all of you have seen a really crappy installation. Not that you've done it, but you've seen it. And you're thinking, holy crap, it's still working. That's because electricity just does that. Okay. It works. Okay. And, unlike things like, plumbing for plumbers, if there's a massive leak, then the water leaks and the pressure ultimately at the end result drops down. And again, then it's a noticeable thing. But with electricity, if you bond things improperly, then you run the risk of energizing constantly metal parts that are conductive, obviously, and the system just continues to work until somebody comes in contact with it, and then something happens and it becomes a hazard. So it might literally sit there for years as a ticking time bomb, and nobody knows any different. If you have a plumbing leak, eventually something rots or something brings attention to it. But with electrical, it does not. So you have to do it right. And there's no substitute for doing it right the first time. I tell people all the time, I don't get paid to do things twice. I get paid to do it right once, right? And so that's the concept that I've always taught. Do it right once, take the time to learn it, and be successful at it. And so that's what we're going to kind of focus on today. Remember, we haven't lost topic. I'm just trying to give you the basics, and we're still continuing with the basics. So again, if you want to fast forward, you can fast forward. But again, to me, whether you like my videos or podcasts, whether they're long or too long, or I'm too detailed, or I ramble on, it is my style. I am not stopping. You can thumbs down me if you like. I don't really care. This is my method. You either have to take it or leave it. I am not like other educators. I'm just keeping it real. So now we know that other articles can apply. So the first thing that we need to do is set the stage. So in the system, you have what's called grounded systems, and you have what's called ungrounded systems. Now, in our case, most of the buildings that we deal with, electricians, of course, you can't have ungrounded systems. A lot of industrial facilities have ungrounded systems. There are some reasons why systems are ungrounded. Sometimes, like in big industrial facilities, grounded systems will trip devices right away. Ungrounded systems will allow things to fault out and still continue to run so that you have a proper shutdown procedure and it doesn't cause additional hazards as part of of a process that they have. But again, you're still going to have a phase-to-phase fault and you still would trip a device. So again, there is some elements in there, but it's an ungrounded system. And there are applications for ungrounded systems, okay? And what we're going to talk about today are grounded systems. So I have a transformer at the utility pole. I have a grounded neutral conductor. It is actually XO. It's connected to the case and through a system bonding jumper maybe, or in the case of a transformer, it's made a direct connection to earth, and it has ground rods maybe at the utility pole, okay? Every 200 yards or feet or whatever, they got a ground rod. Okay, so we're dealing with a grounded system. So coming into our building or coming into our situation, we have a necessary need for a grounded conductor. And a grounded conductor is a conductor which is intentionally grounded, okay? So again, just setting the tone, not going too deep. We're just setting the tone first. We're dealing with grounded systems. So what we have is an overcurrent device that is supplying a branch circuit in our examples today to, let's say, a parking lot lighting pole, or even if it was municipal and they had a street light or something. The premise here is that we have an overcurrent device upstream. Now, granted, street lighting and things, utilities and things like that, they do a lot of things that are unique, okay, in their industry. But today's lesson, okay, so I don't get the haters out there because, they're everywhere. We're talking about a situation where whatever it may be, we're going to talk light poles, things like that, where we have an overcurrent device and it's downstream, the branch circuit supplying the pole light, and something that engineers and designers do that not so sure they understand why they do it or what they're doing it for, but they do it, okay? And that is to drive ground rods at street lights, street signs, as well as parking lot lighting, and even seen it so much as signs on properties as well, where they drive the ground rods. Why are they doing it? We're going to discuss that today. And again, I'm not going to throw my electrician, my engineering buddies under the bus because, again, it's permissible. It's just we want to go back a little bit in history and see what they did and what they used to do and how it's kind of changing a little bit. And then I'll talk about a situation that came up recently so that we can bring context to the whole thing. All right, so the first thing we want to do, as with anything, is we need to understand what are the general requirements for grounding and bonding. Okay, so in this case, we're talking about a grounded system. So in the National Electrical Code, you have 250.4. Now, this is the general requirements for grounding and bonding. These are your general rules, and they're going to give you the code is going to give you some prescriptive methods on how to do things. What terminations you need in 250.8, all these type of things, how to do that. We're going to give you some prescription. Now, the reason that we're going to give you this prescriptive method of how to do things is because it has to make sure that it complies with the performance requirements of Section 4, which is the general requirements for grounding and bonding, why we do what we do. So that's why the remainder of the code, after you get past this section, is going to give you a lot of prescriptive things to do. Do this, do that, do this, size that. We're doing it so that we meet the performance criteria that is here in this section, which is Section 4 of Article 250, which is titled The General Requirements for Grounding and Bonding. It's kind of the saying why we do what we do. So let's look at it. And again, we're going to focus on grounded systems. We're not going to focus on ungrounded. Just grounded systems episode. So if you're somebody coming in and wants ungrounded, hate to be a hater, but you need to listen to a different episode. That's not what this is about. Okay, this is your general circuit that we would have in most buildings, most structures, most applications where we have a grounded neutral conductor application, okay? All right, so grounded systems. Let's start out. Number one, A1 is electrical system grounding. And again, now we're talking about now performance, what we're trying to do. It says, electrical systems that are grounded shall be connected to earth in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that will stabilize the voltage to earth during normal operations. Okay? So we're making these connections. We're putting in our grounding electrode system. We're putting in our grounding electrode conductor. We're putting in our electrodes. Again, that's going to help with lightning issues, getting it to where it needs to go, to the earth. It's going to help with voltage stabilization, a lot of that which takes place back at the XO connection, back at the secondary side of the transformer. But all these things work together in order to create the electrical grounding system. And so we are going to do everything that we do in the code is to achieve this actual performance requirement here. Okay. Now, of course, there's an informational note reminding you keep things as short as possible. Again, lightning and surges and things like that. Don't like right angles. We don't need it to choke itself out. We need to make sure that this sudden surge or some type of lightning gets to where it needs to go. It doesn't like to go through loops. It doesn't, keep it short. Remember the old saying, the shortest path is a straight line. Keep it as short as possible. Again, it's an informational note. It's just a recommendation. But again, it's a pretty important recommendation. Again, so just kind of heed the notice and think about it. Okay? All right, number two. Number two says grounding. Okay, we're talking grounding now. We're not bonding. We're grounding. Grounding of electrical equipment. It says normal, non-current carrying conductive material enclosing electrical conductors or equipment or forming part of such equipment shall be connected to earth so as to limit the voltage to ground on all of these materials. Now, think about this. For years, people have said, let's change the definition of equipment grounding conductor to equipment bonding conductor. And the premise behind their recommendation, and a lot of big educators are pushing for this, and I think it's futile. It's not necessary. We all know that an equipment grounding conductor, you can call it equipment grounding because its premise is to connect those non-current carrying metal parts like the metal enclosure. It's not designed for that to carry current. Now, it will under a fault condition, but it's not designed to carry current. It's a non-current carrying metal component. The raceways on your rigid metal, your IMC, your EMT, all of that is you're bonding it all so it comes back to the equipment grounding conductor so it all makes it back to the source. Look, you're trying to trip an overcurrent device, right? But you're still also doing what? You're grounding it all to do what? To the earth, so as to limit the voltage to ground on the material. Why? Because back at your panel, your service enclosure, you have the neutral. We'll just go with that, grounded conductor. So in our case, it's a neutral. And it is connected with the main bonding jumper to the enclosure, which is connected to the neutral conductor, which is also ultimately connected to what? The grounding electrode conductor that goes down to what? The grounding electrode, direct contact in the earth. So the equipment grounding conductors that we'll learn about, or you've learned about, I have other videos on that, that is providing that connection to earth. So it's meeting this performance requirement based on the prescriptive requirements in 250.122 when we're sizing and doing things with equipment grounding conductors. So when you want to call it a equipment bonding conductor and lose the notion that it is still equipment grounding, it doesn't matter because the moment you change it to equipment bonding conductor, let's assume that passed. Now you're going to have somebody say, well, it serves grounding too. So we need to name it back to equipment grounding conductor. That's why we have put a notation to tell you that the equipment grounding conductor also serves as a bonding conductor. And that's all that's necessary. Let's not over confuse these things. Okay. It does ground and it does bond. Okay. We're not going to find the perfect terminology, but Code Panel 5 does seek out to try to make things as straightforward and accurate as possible, but that would not create any clarity here. Okay. You can agree to disagree, but I don't see where it would because of this statement right here. We're using that equipment grounding conductor to meet the provisions of 250.4A2. And that's what it's doing. Okay. So that's A2, and that's why we run it. That's why we have equipment grounding conductors. That's why we have bonding to do everything we do to try to do what? To take that normally non-current carrying conductor material that encloses conductors and air equipment and trying to establish that connection to Earth. So we do that throughout the system. Okay. So again, you have the prescriptive requirements on how to do that through the various code inside of Article 250. And then you have the performance requirements of why we do it. And this is why we do it. The next one is 250.4A3. Now, A3 is where we kick in the bonding component. And it says bonding of electrical equipment. It says normally non-current carrying conductive materials enclosing electrical conductors or equipment or forming part of each equipment shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. Important word, effective. You're doing it in a distinct manner. Your connections, how you're doing it, following the termination methods in 250.8, following this effective ground fault current path. It's going to also be a low impedance path due to the nature of how you make these connections. That is done with things like equipment grounding conductors. But remember, they also serve a bonding function. But you have the bonding of things together. We have bonding jumpers. Okay, we have supply side bonding jumpers. Okay, we have equipment bonding jumpers. All of these connections that are being done that are going to try to allow what? An effective ground fault current path back to the source of the circuit. And then ultimately back to the source of its creation, the transformer, in order to allow the overcurrent protective device, be it a fuse or a circuit breaker, to function within the parameters that it's specified to function. And so grounding and bonding are synonymous with electrical safety. But they are two different functions. But this is an example of how they work together, for example, in a single conductor. Now, granted, the conductor could be a wire, or the conductor could be an actual raceway, things like that. Again, we have all those rules up in 250.118 that tells you what can be considered an equipment grounding conductor and what not, with the understanding that it can serve dual functions, grounding and bonding, okay? Setting the tone, if you will. Next one we're going to look at is 250.4A4. Now, A4 says bonding of electrically conductive material and other equipment. Now, notice that it says normally non-current carrying electroconductive material that are likely to become energized shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. Now, likely to become energized. The term likely to become energized is a notion that based on the proximity or what it contains, that a certain condition could take place that is likely to energize it. Now, if I have a water pipe in a building, now metal water pipes in a building, if they're all metal, has to be bonded. Okay? But if I have some type of piece of metal in a building and I have a cable that's running near it, some would say, well, didn't you have to bond that metal because it is likely to become energized? And using that as a basic concept of discussion, the question is it really likely? Is it really likely to become energized? I mean, I guess a rat could get there and drag it over next to the metal and chew on it, and then it could, but is it likely? So we don't define the term likely, but I will give you some understanding of likelies. If I have a piece of equipment that has, let's say, it's a water heater, and you'll find out all about this when you go look at 250.104 and things like that. But let's say I have a water heater, and it's got gas piping to it, but it has electric ignition. I have a circuit that contains an equipment ground and conductor in this branch circuit that's running to this gas water heater. Of course, then I have, let's say, gas lines. Now, since the two, I'm using this example now, since the two merge together at a single piece of equipment, the likelihood of those gas lines becoming energized is greatly more enhanced by their close proximity and mutual termination points, or very similar to the piece of equipment. That is an example of something that may be likely to become energized. So when you think of the term likely to become energized, you really have to think, is it likely to become energized? And if the answer ultimately is no, it's not likely to become energized, then there's not a bonding requirement. Although the National Electrical Code does tell us certain things that we are required. Remember, because it is a prescriptive method, later on, once we get out of this section, a prescriptive method, do this, do that, do this, and by doing so, you're going to meet all of these performance or expected performance requirements. See how it works? It's a beautiful thing. If you think about how it works together and how it flows, we're being told that we have to meet some type of performance to save us, to protect us. And then the code proceeds to say, okay, well, you know what? We have enough experience in this industry that if you do it this way, you'll be okay. And that's why we follow it. All right, so that's that one. And then, of course, we're going to end on the fifth one, which is 250.4A5. And this is just kind of a very broad catch me over when it comes to grounding and bonding statement. And because you see the term effective ground fault current path utilized in, again, these different, it was utilized in 250.4A3. And, of course, again, in A4. So we got to bring some context to what it means when we say effective ground fault current path. So 250.4A5 states this. It says, effective ground fault current path. It says electrical equipment and wiring and other electrically conductive material likely to become energized. Now, also think about this. If I have a metal cabinet that I have a panel board installed in it, again, the panel board's the guts. The cabinet is the cabinet. So what you see in your house with your main breaker and all that, the center guts is the panel board. The actual enclosure that it holds is referred to as a cabinet. It goes inside. The panel board goes inside of the cabinet. Now, because of the nature and proximity and how that is, that metal enclosure, that cabinet is likely to become energized. I mean, if something's going to happen, if it happens there, that's what's it's going to energize it. That's another example of what we might consider likely to become energized. All right, so anyway, I hate to digress, but sometimes it's in points that I like to make here. So again, likely to become energized shall be installed in a manner that creates a low impedance, circuit facilitating, and operation of the overcurrent device or ground detector for high impedance grounded systems. Again, high impedance means there's some type of impedance placed in the connection. So again, many people say that is not really to be a grounded system, but again, it makes a statement here. So a ground detector application in grounded systems, you'll have, again, the overcurrent device that we've been talking about earlier. it says that it has to be able to be low impedance circuit. So the connections need to be good. You need to do it properly, follow 250.8, all of those things, so that you create that low impedance ground fault current path. Okay. Now, in doing so, it says it shall be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault may occur to the electrical supply source. The earth shall not, now this is important, and I tell students all the time, and this will play a huge role in our discussion today when we talk about ground rods and what they are to do and what they're not to do and the confusion around it. It says right here, and I tell students, if you can highlight in your book, this is something I highlight. The earth shall not be considered an effective ground fault current path. Now, utilities use it all the time because it's all relevant to the voltage level, right? So to illustrate that, I tell people, okay, so let's assume that out on the primary side of your transformer, I'm kind of going to give you some context here on why the earth is not, and it'll play a part later on. So let's say that the primary side in our utility in our neighborhood, is say it's stepped it down through the neighborhood. Let's say it's down to 7,200, okay? And that's the primary, and it's going to kick it down to a 240/120 for the secondary. All right, so let's do a little math. So let's get our calculators out, and let's just kind of give you an understanding on why ground rods work for utilities, but they do not work for what we do when we're on the portion of the system at the service point where the demarcation line is now the NEC kicks in and the electrician has to deal with everything around the premise. Okay, so give you an example. So let's say utility transformer primary side is 7,200 volts. And now we're going to step it down to 122/40 and we're going to bring it to our premise. Now they got ground rods out at the actual poles. Okay, so let's look at it. So if you use a little Ohm's law, you're going to see that 7,200 divided by 25 ohms, which is, again, let's say it's a perfect world where we have a 25 ohm ground rod, then that would be 288 amps. Now, 288 amps will easily clear the fuse that's on the primary side of this utility transformer. Okay? That is not a problem for them. That's why they do what they do. This is why they use the earth, okay, in their layout. But for us, it's so important to understand why we can't use the earth and why 250.4A5 is telling us the earth is never to be considered an effective ground fault current path. The impedance is just simply too high. So in this case, it was 288. Now, think about it. On our side, let's say we have a typical branch circuit and it's 120 volts. And we have a ground rod. Let's say it's a perfect world. The ground rod is 25 ohms or less, so we didn't have to supplement it. We can just go with the one ground rod per the code. And so at this point, we just simply take 120 volts, divide that by 25 ohms, and that is 4.8 amps. Well, 4.8 amps clear a 15 amp overcurrent device, which typically is the smallest size overcurrent device in your dwelling or your building. Will it trip it? Absolutely not. No chance. Next, what if somebody says, well, what about if it's a 240 volt circuit? Okay, well, let's do that. 240 volts divided by 25 ohms. It's 9.6 amps. Still, no chance at clearing a 15 amp overcurrent device. Much less the chances are that 240 volt circuit is probably going to be on a 30, 40, or even a 50 amp overcurrent device. Not even close. Not even close. So this is an example of why you would never use the earth as a return path to clear any devices, period. It's just not something that you would do. And so when we meet the prescriptive requirements of the NEC, we're going to meet the performance requirements of the NEC. And that's why they work together so nicely. Okay, so now let's move on to the scenario. So in this case, I want to kind of jump to now the situation because we understand that we can't use the earth. We kind of followed 250.4A1, 2, 3, 4, and 5. We set the tone. Now we want to jump to a situation where we're dealing with the question at hand on today's episode. All right, so what we've got is it's very common in the industry for the years when we had things like, and we're going to keep it directly at our issue here, where we had post lights, pole lights out around a parking lot. Of course, this could also apply to street lights, to street signs, things like that, if they're on the load side of a overcurrent protected device. So that's kind of, again, setting the tone. We're not talking about what a utility might do, what they're permitted to do on their scope of the National Electrical Safety Code, or what the street lighting codes might be. We're going to have the concept of, well, we know that it's an electrician-controlled overcurrent protected device. They're the ones that put it in. And we're talking about branch circuits that are going out to these specific, for example, in our example, a pole light out at a parking lot. Okay. So now, for years, what we've seen is designers will say, I want to have ground rods driven at that light pole. Now, again, don't get me wrong. If we're talking about a huge tower and all those type of things, and there's reasons that they do ground rods and triads in order to get the ohms of resistance so low that when lightning strikes the system, because again, lightning's all about proximity, that it's going to funnel it to the earth where it's trying to go, and it doesn't create other issues in the system. Okay, we get it. Side arcing, things like we get what they're doing this for. So that's not what we're talking about here. A very common practice at things like towers, transmission towers, and everything like that. We're talking about light poles. We're talking about parking lot lighting poles, which I see it more often than not, and we'll use that as the example because that's kind of what today's episode was about. Whereas at the parking lot light pole, they drive ground rods. And it's driven by the fact that the engineer or the designer specified that a ground rod be driven. Now, hopefully to this point, we speed forward a couple decades and we understand the importance of having an equipment grounding conductor run with that circuit, because that is what's going to facilitate the operation of an overcurrent protected device. We get that by now. We're required to run an equipment grounding conductor. We just saw that why we do this, right? And the prescriptive method of doing it, how we run things, meets the performance requirements that we just discussed. We get it. But routinely, we still see drawings where you have these base concrete bases with rebar in it, and you mount the pole light to it, and they'll require ground rods to be driven. So let's talk about a little bit of maybe some of the reasons why designers might specify this. And then we'll discuss whether or not it's a legit or a fallacy in their thought process. Number one, there are some that will say that if I install ground rods at the pole light, for example, that lightning will be less prone to strike it. False. Lightning is about proximity. It doesn't know whether or not that is connected to the earth or not. It's irrelevant. It is all about proximity. And again, as it starts to discharge, then it's going to look for a conductive medium that's going to allow it to get where it needs to go. And so just because we drive rods at a light pole does not mean that's going to prevent it from getting struck. Okay, so that's a first fallacy, right? Next, they'll say, well, we're doing it because if lightning does strike it, it's a less of a chance that it will damage the concrete base of the light pole. Again, yet another fallacy. Now, we have to remember that most of the situations of these light poles, the base is concrete and it's usually constructed of rebar. It very much acts like a concrete encased electrode in its concept of rebar in connection with concrete, in connection with earth. Typically what happens, again, whether you're doing it with like a sterno tube or something, you still have a portion of the concrete in it that's going to be in contact with the earth, which is in contact with the rebar. There's enough surface area that this is not going to be an issue. Okay, not going to be a real problem. And at the end of the day, it is not inherent that lightning striking the pole is going to cause the base to just blow up. I ask for you to give me any evidence of that because I have not seen it. Okay, so again, I'm gonna call BS on that and say that's another. I don't buy it. And as we saw earlier, when we used the example of 7,200 volts for utility and ground rods, for example, or whether we use the simple premise wiring 12240 application, the ability for it to clear an overcurrent device has nothing to do with the ground rod and nothing to do with its placement in the earth. Okay, we're all clear on that. And again, if you don't believe me, it's simple math, right? Is a simple concept. So then I always have somebody out there that says, yes, Paul, but we're dealing with 480 volt circuits most of the time. Okay. Well, 480 divided by 25 is 19.2. When you're dealing in that type of voltage, you're in commercial. And typically the smallest overcurrent device is 20 amperes. It ain't tripping the breaker. Now, even if it is 480, it can almost a greater chance that the breaker's rated higher than 20 amps anyway. Come on, man. Let's think about this a little bit. Let's use a little common sense. We just do not use the earth. And it told us that right in the performance requirements. It says, I don't care what you do. That's not why we're connecting to earth, to clear devices. That's not why we're doing it. We're doing it so that we can have a situation where everything is doing what? It's designed to limit the voltage to ground on different materials. It's designed to help stabilize the voltage to earth during normal operations. It is not being done to clear a device at all. Okay, so moving forward. So let's say that you design a light pole, and again, you can translate this to any other situation you want where you have a branch circuit and it's feeding something and it's a branch circuit and they want you to drive ground rods. Okay, let's hope that we have an equipment ground, run with all this. But in the incident, let's talk about some other things. Now this is where I say to my electrician and my engineering friends that we can get along on this topic, because the National Electrical Code does not prohibit me from putting in that electrode. It does not prohibit me from making that connection from that pole, metal terminal point, even the equipment grounding conductor point, down to the electrode. It's okay. Nothing prohibits it. A lot of people say, well, you can't do that. No, I'm going to tell you why. Because even though we want to make sure that the engineers are not using that to try to clear any overcurrent or even think that it provides any type of safety to it, they can do it because that's called what's an auxiliary electrode. Now, in the industry, we do auxiliary electrodes a lot for pieces of equipment in buildings that has some type of motion. It creates static electricity, and we want to discharge it. That's very common. Of course, in this case, there's no moving parts. That's not why we're doing it. But if they want to require an auxiliary electrode, just remember that and a lot of inspectors will get confused, it's auxiliary. It's in addition. It's not required. It's permitted. And we'll look at that in a second, but that's a permitted electrode. Now, a couple key points to remember is it's not required, it's permitted. So since it's permitted, it's not required to meet all of the general rules that you would have for a normal, let's say, grounding electrode that you would for like a dwelling or a structure. It is different. It's an auxiliary electrode. So in your code books, this is when we got to take a little bit of a gander, and we have to go up and look at the requirements in 250.54. Now, 250.54 is talking about auxiliary grounding electrodes, and that's what we're talking about, all right? Because all of the required electrodes are in 250.52, and all of the methods of installation for ground rods, for example, because that's kind of the topic of today, is 250.53a, and it'll give you, again, how to do it and whether or not you have to supplement it or not, if it meets 25 ohms or less, and you have all that. But this is an auxiliary grounding electrode. It's not required. It's the engineer is designing it in, and of course you got to follow what the engineer wants. But as long as they're not doing it as an attempt to substitute the necessary need for an equipment grounding conductor that's run with the circuit conductors, then it's okay to have this auxiliary electrode. But let's read the code. 250.54. It says auxiliary grounding electrodes. It says one or more grounding electrodes shall be permitted. Okay, we're talking auxiliary ones now. Shall be permitted. That's an important statement. Shall be permitted to do this. Okay, to be connected. Now here's where people get confused. It says auxiliary grounding electrodes, one or more grounding electrodes shall be permitted to be connected to the equipment grounding conductors specified in 250.118, which is our list of what can be considered equipment grounding conductors. And it says, and shall not be required to comply with the electrode bonding requirements in 250.50 or 250.53C. Okay? So it doesn't have to meet all of those rules and that. And here's another important thing it says. Okay, all those things that we have to meet with normal ground rods or normal grounding electrode applications. It also goes on to say, or the resistance requirements of 250.53A2, which if you go back, that's that 25 ohms rule. So guess what? This auxiliary doesn't have to meet the 25 ohms. If you drove it and it's 500 ohms, it doesn't matter. It's auxiliary, which is typically why engineers will specifically give a certain level of ohms, because they understand that hopefully that this is auxiliary and that it's not required. Now they might be requiring it for whatever. They're the designers. They know what they feel they know what they're doing it for. And it is a big deal with towers and things like that because of the other side effects that can happen from lightning strikes and the propensity of it being struck due to its proximity and size and whatnot, that they have their own rules they like to follow. Whether they're required or not is irrelevant because the engineer specified it. So in this case, irrelevant to the fact that it's not required, if the engineer requires that you do it, okay. But just remember, it doesn't have to meet all the typical rules that a normal electrode would be. Okay. Now, the other thing, you have to go on. It says, for the exception, it says, but the earth, again, shall not be used as an effective ground fault current path as specified in 250.4A5 or 250.4B4. And again, the B is ungrounded systems. So, look, the code is making it very clear. If you want to do it, that's fine. Just make sure you understand why you're doing it and what it's not intended to do. So, other thing is, I don't have to follow these rules. I don't have to follow the sizing requirements for that grounding electrode conductor. Essentially, it's really a bonding jumper. I don't have to follow those rules. That's why it says that you don't have to meet the requirements of 250.53C. Okay, which is for bonding jumpers. I don't have to meet that. I don't have to size it, right? In the same way I would a typical ground rod application in 250.66. I don't have to do all that, right? So, again, important that you understand what an auxiliary grounding electrode is, that the engineer knows why they're installing it, what benefit they're going to get out of it, and then they have to understand what they're not going to get out of it. So we had a recent situation where I was asked a question. An engineer specified ground rods at these light poles, every light pole, and he wanted the ohms to be down below a certain value. So again, it caused the electrician to have to drive multiple ground rods and ground rods, and they actually piggybacked them on, one on top of the other and drove it to a certain distance to get a certain ohm value because that's what the engineer wanted. And interesting enough, it was just a light pole. So again, it must have been a very important light pole, if you will, because they also required lightning arresters to go from the connection onto the metal pole over to a lightning arrestor, which ultimately, from that lightning arrestor, it also connected to the ground rods. But even though the circuit had equipment grounding conductors, that equipment grounding conductor also connected to the ground rod, which in this case was an auxiliary. And of course, you saw the code permits that. It was unique how they did that because they required them to CAD weld them all to the ground rod. Most of the time, what I would see is the circuit conductors and the equipment ground run to the post light, or the pole light. And then there's lugs there, that the lugs are installed in accordance in 250.8. And then from there, you go from that connection, the equipment ground will connect to the pole light, meeting the bonding requirements. And then from there, it would make a connection down to the, if you were going to use the auxiliary, and make a connection down to the actual ground rod. And the size of that connection, that bonding jumper, whatever you wanted, whatever they specified, if you will. Most people would do the same size if it was an grounding electroconductor. They would choose a 6 and copper and keep it simple. But again, nothing dictates the size. And they would tie them all together that way. Well, this unique application, they wanted everything tied back to the ground rod. Now, the only problem I'd have with that is I would want to make sure that the equipment grounding conductor actually goes with the circuit conductors all the way to the pole, into the pole, and then any connections subsequent to that could go to the ground rods, making that connection. Ultimately, it's not necessary if you were to go from the equipment ground terminal inside of the pole and then run down to the ground rod. Then ultimately they're both connected to the equipment ground inside of the piece of equipment, and that would be fine too. That engineer just had a unique way they wanted to do it. And again, I'd have to see it to say whether or not I like the concept or not. But here's the important thing. He didn't need the electrodes, but for some reason they think that it benefits the system. That's fine. That's their prerogative. What's more important is that an equipment grounding conductor was run. That is what's going to cause, if any of the parts get energized, that's going to allow me to potentially clear an overcurrent protective device under a short circuit, ground fault, or overload condition. I am still going to protect somebody who could come in contact with that system. Now, for them, they were also concerned with lightning, and that's why they wanted the lightning arrestor in line with the system going down to the ground rod. Fine. That is something that they can specify. And I told the listener, I said, that's fine. The code provides for that. They can do it if they want, as long as, again, they have an equipment grounding conductor and everything as far as the circuit reliability is there. They're meeting, they can have the prescriptive requirements. As long as they meet the performance requirements, it's okay. But you can see where this would get somebody confused. All right? Understanding that is an auxiliary electrode, and everything that they do after they meet the basic requirements is permitted. You can do it. Okay? So hopefully you got something out of today's episode. It's just kind of an analysis, a good refresher, if you will, on grounding and bonding. Kind of a refresher on the concepts. Kind of get our feet wet back into what the actual performance requirements are of 250. And then what the prescriptive requirements are to meet those performance requirements. It's a beautiful thing. Hopefully you got something out of it, folks. Till next time, stay safe. God bless.